tonight?
Good, how about you?
Good. So what are we doing tonight? Did you send me anything, or are you going to verbalize it?
I'm about to send you something, actually.
Okay.
One moment. Here you go. I sent it.
Internet's fast tonight.
That's good.
Because sometimes it takes a while.
Yeah, like last time.
It doesn't always get here lickety-split. All right. Let me put that on the left and that on the right. All right. These problems. Uh-oh. What's going on with my pen here? Hold on. Computer is acting up a little bit here. Not used to seeing it act up. There we go. No, my pen still isn't working. Hold on. Try one other thing real quick.
Okay.
At least I can see it now. Let me open it one more time. There we go. This may look like a log problem because the variable is in the exponent, but in this particular case it isn't a log problem. It's actually easier to solve if we can find a common base, a common exponential base. So, and we're looking for numbers that relate 8 to 64. So what's the common base?
8.
Yeah. So I can write 64 as 8 squared in parentheses, and that's to the x plus 3. And if that's equal to 8 to the 2x minus 9, now apply the rules of exponents, and what do you get on the right side?
2x plus 6.
And now, because we have the same base, we can equate the exponents. So now you can say 2x minus 9 equals
2x plus 6. So then I would add a 9.
Well, now hold on a second. That's an impossible solution. In other words, the 2x minus 9 cannot be equal to 2x plus 6.
True.
Interesting. So that tells you that there is no value of x that makes that proposition true. What's it say at the top of this page here? Right above where it says round off to the nearest hundredths. What are the primary instructions?
Simplifying. They're solving the equation for x.
Okay. Interesting that the very first one they would give you would not work. All right. Well, let's not worry about that. I don't think I made a mistake, did I? 8 to the 2x minus 9 equals 8 squared to the x plus 3, which is 8 to the 2x plus 6. Yeah. Okay. So that tells you there's no solution for that one. This one, what's the common base in number 2? How can I express 8/27 in terms of 2/3?
2 cubed.
2/3 cubed.
2/3 cubed.
So the left side is this, and the right side is 2/3 cubed, all of it, to the 3x minus 4. And now, seems like my audio might be going in and out too. You still there, Taylor?
Yes.
Okay. Now when I do the multiplication, I get 2/3 to the 3x plus 2 equals 2/3 to the 9x
minus 12.
minus 12. In other words, I have to multiply these two exponents. 3 times 3x minus 4 is 9x minus 12. And now that is solvable. On the left, I'm going to end up with 3x plus 2 equal 9x minus 12. You can always equate the exponents if the bases are the same. And now that can be solved. 6x equals 14, x equals 7/3.
Okay.
Okay. Okay, log problems. Let's use the property of logs. How can I take the left side of this equation and turn it into one log function? If I told you the log of A plus the log of B, that's the same as the log of A times B.
Okay.
With this one, put them back together, and what would it be? It would be natural log of what?
Natural log of 10 or 1.
No, multiply the two arguments, so it'd be the natural log of x plus 1 times x.
Okay.
And I've turned it into one log function now, instead of two. And now you can multiply that out so that I have the natural log of x squared plus x equals the natural log of 2. And now, again, I can equate the arguments. You can kind of think of it as dividing both sides by natural log, but that's not anywhere close to what you're doing, because it's not like the natural log is multiplying this. It's a function. It's more like f of x. It's the natural log of that, but as long as it equals the natural log of that, then I can say x squared plus x equals 2. Let's solve that.
Minus 2.
So I get x squared plus x minus 2 equals 0, and then what?
X plus 1 and x minus 2.
Almost.
Or x minus 2 and x plus 1.
X plus 2, x minus 1. In other words, the bigger of the factors has to go with the positive sign, has to go with the sign of the middle term.
Okay.
If you do your double smiley faces, you'll see plus x becomes the middle term. But logs are particularly vulnerable to extraneous solutions. Notice what my two solutions are here. X equal 1 and x equal minus 2. Well, if we go back to the original problem, Not this. That was the second step, or the first step. You have to go back to the original problem and test for domain violations. Notice that the -2 violates this domain. You cannot take the log of a negative number. So that's an extraneous solution, and the only solution that works is x equal 1. And that happens almost all the time with log problems, is that you end up, especially if you end up solving a quadratic, you end up with two solutions and one of them isn't valid because it violates the domain. Here's
negative.
What's that?
It's because it's negative, right?
Correct. But notice that if I would have checked and plugged in -2 to that part, it doesn't violate it. When I plug in -2 for x here, I get a -1 times a -2, and it turns the whole thing positive. So what it's telling you is that what I've circled here is not absolutely identical to the original problem. It's just one step in the solution. And that's difficult to explain why they're not identical, but you always have to go back to the original problem. You cannot check your domain restrictions from that step there.
Okay.
All right, number 4. Notice the relationship between those two bases, 5/6 and 125 216ths.
5 cubed
Okay.
would be 125.
So I've got 5/6 to the 2x on the left, and I got 5/6 cubed, both top and bottom, to the 7x minus 7. So what's the next step?
Multiply 3 times the other exponents.
Okay, and then what?
21x minus 21.
Okay, and then what?
Equals 2x.
Right. In other words, 2x equals whatever the product of that is, which is 21x minus 21, and this is going to have a solution. That first one was very strange because you end up with 2x in both instances after you do everything. Gives you no solution, but this solves easy enough. From here, we don't need to keep going, right?
Yes, we don't.
Let's go to number 5. 6 plus 2 log of 2x equals 10. Well, to solve a log equation, isolate the log and then put it into exponential format. So our goal is to get that equal something, and once we do, we'll then be able to put it into exponential format and then solve it. You'll see. So what's the first step in isolating that?
I would have to get rid of the 6 on the left.
Next step?
The 2 in front of the log, would I divide everything by 2?
So now we have the log of 2x equals 2. And let's put that into exponential format.
Okay, so it would be 2 log x equals 2.
No. Let's go over that.
Okay.
Y equals b to the x. For example, a equals 2 cubed. If this is the exponential expression, if I want the logarithmic expression, I only have to remember one thing. Logs are exponents. So I can immediately say that. The log base something of something equals x, because logs are by definition exponents. Well, where's the b and the y going to go?
Um,
B always goes there, right?
yeah.
Only leaves one other place for the y, there. So if I want to take that expression and state it logarithmically, how would I do it? The log what? What's the base? What's the
Log 2, 8 equals 3.
correct? So, and you want to be able to go both ways here. In other words, you want to be able to take an exponential expression and turn it into a logarithmic one, and vice versa. Now, when I'm converting from a log to an exponential, the little ditty that I use to remember it is I take the number on the far left, raise it to the power of the number on the far right, and it's equal to the number in the middle. So 2 cubed equals 8.
Okay.
Okay, so in our problem,
It's a 2.
we've got the log of 2x equals 2. What's this base?
10 automatically.
So put that in exponential expression for me.
An exponential, wouldn't it be 10 log?
10 squared. When you put it into exponential, you get rid of the log.
Okay.
Equals 2x. In other words,
Okay.
I took the number on the far left, raised it to the power of the number on the far right, and it's equal to the number in the middle. That's the way I always remember it. And now it's relatively easy to solve. 10 squared is 100. That's equal to 2x, then x equals 50.
Okay.
Okay, so that's how we're going to solve all log problems, basically, other than ones like this, where you can end up with the log of something on one side equals the log of something else on another, and then you can equate the arguments. But a more typical way to solve log problems is number 5. And let's look at number 6. Hold on. All right. And you can only do these tricks if it's the same base. Okay?
Okay.
So in number 6, what can I say right out the gate?
Log 4, okay, x squared plus 7 equals log 4.
No, that's what you're looking at. But what can you state based on that? Here we have the log base 4 of something equals the log base 4 of a number. So what can I say? I can say that the arguments are equal. I can make that statement.
Oh, since it has the same base. Okay.
Yeah. Yes, it's like divide both sides by log base 4 to get rid of the logs.
Okay, now I see.
All right. Now, x squared is equal to 36. What's x equal to?
6.
No.
What?
Plus or minus 6.
Plus or minus 6, because it's square root.
What 95% of my students make that mistake. And I want to sing them a song that says, whenever you solve an equation by taking the square root of both sides, always, always start your answer with the words plus or minus, because everybody tends to forget it. Now, in this case, does either of those solutions violate the fact that the argument has to be greater than 0?
Yes, the negative.
Does it? What's negative?
Yes, about.
Negative 6 squared is 36 plus 7 is 43. It doesn't violate it.
Oh.
In other words, it only violates it if it makes the argument either 0 or negative. If we go back to problem number 3, remember we had one of the solutions was x equal minus 2. Well, that violates the argument. You can't have a negative argument. You can't even have a 0 argument. So the negative 2 answer had to be thrown out because it violated the domain. But it doesn't violate the domain here.
Okay.
Natural log of x equals 7.5. Remember how we're going to solve every log equation.
You said get rid of the log, correct?
Correct. Convert it to exponential format. What's the base of natural log?
10.
No, that's the base of common log.
Oh, it's, would it be, so it would be e?
E. So what's the equation going to read?
E to the x equals 7.5. And it's 7.5.
No. The number on the far left raised to the power of the number on the far right. So e to the 7.5 power equals x.
And that would be 7.5.
No? E is a number that's approximately 2.71. You'd have to get this number out of your calculator. This is definitely a calculator problem, but one that we can certainly do now. In other words, you can take e to the 7.5 power and come up with a number. Can't do it manually, but you can certainly do it on your calculator. There's a special key for e just like there is pi.
Okay.
What kind of calculator do you use?
TI-84. I believe E is on like the right side.
It's, here I got one, let me have a look.
Is it under the negative sign or something?
It is,
Or division
where the
sign?
pi, you see where the pi key is?
I don't have my calculator on me currently.
It's on the divide key.
Okay.
It's the blue, the second on the divide key. It has a small case e. It's not the capital E, but it's a small case e. But it'll solve this problem for you. Now, 8 isn't particularly tough because what's the common exponential base we're going to convert 4 to?
4.
How we?
No, 2.
4?
2 squared.
Right. And then we're going to multiply the exponents, set them equal to one another, solve. Let's do 9. I suspect you're going to have more problems with questions like 9 than you are questions like 8.
Okay. So 9 minus 3.
Okay.
So then bring me to 3 log 2x equals negative 12.
Okay.
Then divide both sides by negative 3.
Okay.
Then change it to exponential form.
Which is, for this one?
10 squared equals 4.
No. The number,
Yeah.
the base, raised to the number on the other side of the equation equals the middle. Well, what's the base?
2?
No. Common log.
10.
10. So what's the equation? What's the exponential format?
So you said I put the opposite or whatever it equals to, so would that be a 4?
Make sure you're seeing how I get that. In other words,
so
there's an implied 10 there. If there's no base written, it's 10 or E if it's natural log. Otherwise, the base will always be written. So I always take that number, raise it to that power, and it's equal to the number in the middle, the argument. Okay? 10 to the fourth is 1 with 4 zeros. That's equal to 2x. Now you can solve it. X is 5,000.
5,000.
Mm-hmm.
Okay.
So the secret to all the log problems is to isolate the log and then convert it to exponential format. I tell you what, let me give you, since we have 5 minutes, is that all the problems on this page? I'm not missing it, am I?
No, that's it.
Give you a little bit of a harder one here.
Okay.
Would you do this one? Same exact kind as you're getting, only it's a little harder because of something. What's the common exponential base?
9.
Not really.
Or no, 3.
3. In other words, I have to be able to write both of these numbers in the same base. I can't write 27 as 9 times 3. I mean, I can, but it doesn't help in solving this problem. But if I convert these to their common exponential base, which is 3 squared
and 3 cubed,
x plus 2 equals 3 cubed times 4x minus 1. Now do the multiplication on both sides, and you get this.
2x minus 8. Wait, hold on, I messed up the sign. A plus 8.
As long as you get to this, plus 4.
Yeah, plus 4.
Okay. Now you can equate that equals that and solve it easily.
So then I'll do plus 3 minus 2. And that would be 10x.
Well, I just made this one up off my top of my head, so I don't even know if the answer is an integer or what. But yeah, the only thing more difficult about this problem than any that you had was the fact that everyone you had, the common exponential base was in the problem already. In this case, it was 8. In this case, it was 2/3. In this case, it was 5/6. Whereas in this problem that I gave you, the common exponential base was not there to begin with. We had to find it. We had to figure out how to relate 9 and 27, not by multiplying or dividing them, but by finding their common exponential base.
Okay.
Okay? All right. Just make sure that you can go both ways on, tell me again how to write that logarithmically.
Logarithmically.
Start with log. What's that?
I was asking if what numbers you want me to use per se.
Don't use them. Use the letters.
Okay, so then I would put the y next to the log.
Okay.
On the bottom.
Let's talk terminology for a second. That's the base. That's the argument.
And then equal to x.
Right. And like I said, the only thing you ever have to memorize is that logs are exponents. If logs are exponents, then I can immediately state that. And then figuring out where the b and the y goes is pretty easy. The b always goes down here. Only place the y can go is there. And be able to go both ways. You have to be able to go both ways. They're going to give you some equations that are exponential, some that are logarithmic, and you usually have to do the opposite. In other words, you have to convert them in order to solve them from one to the other.
Okay.
Okay? All right, Taylor. Have a good rest of your evening, and I will talk to you next time.
Okay, sounds good. Have a good evening. Bye.
Bye-bye.